Hello friends, myself Chandra Kumar. I am taking electrical machine design for the 7th semester students of electrical engineering. In the previous lectures, we will discuss about the transformers basic parameter. Now we will discuss about the overall dimension of the transformer. Net iron area or the total is having the net iron area of the lag or limb or core AI, it will be pi upon dm meter square. For a given area AI, different types of core sections that are used in practice are circular type, rectangular type, and the square type. So whenever we are saying or the choice of the core section, we are finding that it may be a circular in nature. So if the circular in nature or if the circular core is there, if the area, if we are assume that it will be 10 centimeters square, then the diameter of that core, it will be 3.56 centimeter, and the circumference of that, it will be 5 into 3.56 means 11.2 centimeter is the circumference of this type of transformer, this type of core of the transformer. Whenever we have to just think about the square core, then and we are assuming that the same area will be there as the 10 centimeter square. Then the side of the square it will be the square root of that. So it will be 3.16 centimeter, and the perimeter of this one it will be 4 into 3.16 means 12.64 centimeter. Similarly, whenever we have to just take this one as a rectangular core for the iron area as a 10 centimeter square, then the perimeter of this one it will be 10 plus 1. If we are assuming that it will be 10 centimeter wide and 1 centimeter will be height of the contour of the core, then at that moment it will be 10 plus 1 into 2 equal to 22 centimeter. If the sides of the rectangular are assumed to be 10 centimeter and the 1 centimeter. So you are finding that the circumference of the of circular core it will be 11.2 centimeter. If we are looking over the parameter, in the case of the square it will be 12.64 centimeter. If we are taking it as a rectangular of the same area, then the size will be 22 centimeter. So it is clear that the rectangular core calls for more length of copper for the same number of turns as compared to the circular core. Therefore, circular core is preferable as compared to the rectangular or the square type core. So mechanical forces we are measuring over this side, whenever we have to just take the square type core, then the mechanical forces circular coil on a circular core, it will be outward in the format. If we are taken it a round coil or a square core, then it will be like this, and the force will be along this one side. And over here we are finding that it will be the equal, but on in this case it will be not a equal. In case of the square coil or a square core, then we are finding that the force will be this way. It will be perpendicular to the core. And whenever we have to just look over the circular coil on a rectangular core, then the forces it will be maintained in this type of structure. And in case of a rectangular coil of a rectangular core, then the forces it will be like this. So that will be the basic difference whenever we have to just look over the side, that this type of core we have to form while we have to make the transformer. So it's not a simple task for you to just make a square type of circular, square type or a rectangular type or a circular type to go for and make the transformer. So we have to just think about that thing, that is how we have to minimize the forces we apply over the transformer while it will go into the working condition, because it will be increased or decreased as per the size of the transformer. So very high values of mechanical forces under short circuit condition tries to deform the shape of the sphere or rectangular coil. The mechanical forces try to deform to a circular shape and hence damage the coil and insulation. Since this is not so in case of circular coils are preferable to square or rectangular coils again. Thus, a circular coil core and a circular coil are preferable in nature. Since the core has to be of laminated type, circular core is not practicable as it calls for more number of different size laminations and poses the problem of securing them together is in position. However, circular core can be approximated to a stepped core having infinite number of steps. Minimum number of steps 1 and the number of steps in practice is limited to a definite numbers. Whenever a stepped core is employed, a circular coil is used. So this will be the case whenever we have to just look over that side. That it will be the laminated circular core and this will be the stamped core approximately to a circular core. So leg or limb section details, it will be finding over here. The different types of leg sections are used as rectangular, square and the stamped format. So the same rectangular core with a rectangular core, we are finding that if A it will be the width and B will be the height of the core. So leg of a core type transformer, it will be this, and the central leg of a cell type transformer, it will be like this. So where this size will be the twice of A. A is the width of the stamping or leg, B is the gross thickness of the assembled core or width of the transformer. AI is the net iron area of the leg or limb or core. So A is A times AI equal to A times KIB for a core type transformer, where Ki is the iron factor or stacking factor. 2A is the width of the central leg in case of the cell type transformer. B is the width of the transformer, so the AI equal to 2A times KIB for a cell type transformer. Similarly, whenever we have to just look over the square core type with a square coil. So the size will be the A or A, both are the A, width of the leg and the width of the transformer will be the same. So A equal to PI A square, twice of A width of the central leg for the cell type transformer, so twice of A. So AI equal to PI times twice of A square for a cell type core transformer. For a square core type where the size, length and the square will be the same, but the whenever we have to just look using a circular coil, so it will form a diameter. So the A width of the stamping or lag is equal to the D sine 45 degree. So D cos what or D cos 45 degrees. So 0.71 D, where D is the diameter of the circumference in circle. So AI equal to KI times A square equal to KI 0.71 D whole square. So it really comes out around for 10% insulation. We are saying that it will KI equal to 0.9. So the size of this one, or the area of this one is the 0.45 D square. And therefore the area, whenever if we just compare all the previous one, we are finding that there is a variation of the 57.3%. It is clear that AI is only 57.3% of the copper. Rest of the area, 42.7% of AC is not being utilized usefully. In order to utilize the area usefully, more number of steps is required. This leads to 2-step, 3-step, etc. core. Cruciform or two-step core. A is assumed as the width of the largest stamping, B is assumed as the width of the smallest stamping. So the gross area of the core AG equal to AB plus twice of B into A minus B upon 2. So it will be comes out to AB minus B square. Since A equal to D cos theta and B equal to D sin theta, we are finding that the value of the in order AG is maximum, while we have to just differentiate it in respect to the theta. So we are getting that the value of the tan to theta equal to 2 or the theta will be the 31.7 degree to find out the maximum condition. So as per the formula we are using, the same formula we are applying over here and we are getting there is the change of this one to 71% while we are using the this type of arrangement for making the core of the transformer. It is clear that addition of one step to a square core enhances the utilization of more space of the circumferencing circle area. Next will be the three-stepped core. Width of largest stamping A is 0.9D, width of middle stamping 0.7D, and the width of the smallest stamping C is 0.42D. area will becomes of 0.6 d square. Width of the four-step core, width of the largest stamp is 0.93 d, and similarly the area AI comes out 0.62 d square. As the number of steps increases, the diameter of the circumferencing circle reduces. So the cost of the core increases, cost of copper and size of the coil or transformer reduces. Next will be the yoke section details. The purpose of the yoke is to disconnect the legs, providing a lead reluctance path. In order to limit the iron loss in the core in the yoke, operating flux density is used by phasing the yoke area. Generally, yoke area is made of 20% more than the leg area. Notable point is that whenever the yoke area is different from the leg area, yoke can consider to be of rectangular type for convenience. In general, the height of the yoke Hy can be taken as 1 to 1.5 times of A. When there is no data about the yoke area, consider Hy equal to A. So this will be the shape of the yoke. Then we find that the yoke may be the rectangular like and yoke cruciform leg and yoke and rectangular yoke and the cruciform leg. So this will be the structure of the yoke can be available for the system. So that the different types of yoke sections use the square type, rectangular type, and the tuck form. Next will be the area of the window and the core proportion for this one. Actually, the formula for this one that for the single phase it will be 2.22 or 3.33 or 6.66 F del AI DM AW into 10 minus 3. So if HW is the height of the window, WW is the width of the window, then area of this one is the HW times W. In order to limit the leakage reactance of the transformer, HW is made more than W. In practice, HW by HW oblique WW lies between 2.5 and 3.5. So this will be the status of the core whenever we have to just make about the window of the transformers. And this may be the square or the rectangular core width or square or rectangular coil. This will be the stepped guide uses only for the circular coil type. And this will be the arrangement we are discussing, which will be saying about the transformer. That's what we will do in this case.